Hello, welcome to Econometrics Melody. In this video, we will discuss about the independent events. Now, let us say from the Venn diagram, we know that set A, it constitutes of the elements of A, B, and then set B, it contains the element B, C. This A, this is equal to everything that is in A but not in B. So we write it as A, B complement, and then we are done with this A. Now let us try to write this B. So B is equal to, let us write union and A, B. So this is B. This set A, it contains all the elements of A and that does not belong to B, and it contains all those elements of A and that is common in B as well. Similarly, we can write B as all those elements that are common in AB as well as the elements does not belong to A but that is a part of B. Now let us concentrate on A. Therefore, A can be written as, this is the set notation, is AB complement union AB. And then let us take the priority. Let us write the priority counterpart. So priority of A is equals to priority of this union this. So when we have a union, let us apply the addition rule. This is equal to AB complement plus priority of AB and then minus priority of AB complement intersection AB. So we have applied this formula. The event AB complement and AB, these two events, they are actually mutually exclusive. So this, let me circle it. This is represented by AB complement, and this part, it is A intersection B, it is AB. So these two events actually they are mutually exclusive, meaning that there is no common region, there is no overlapping region. That is why this part, it should be equal to 0. Priority of A, this is equal to priority of AB complement plus priority of AB and then minus AB complement and AB, so it is 0. Therefore, priority of A is equal to priority of AB complement plus priority of AB. Priority of AB complement, so this is equal to priority of AB complement, this is equal to priority of A this minus priority of AB. So we got this relationship, and here we are going to make an assumption. So in our previous video we have already said that when the two events they are independent, then their intersection, the priority of their intersection is equal to the product of their individual priority. If we can ensure this multiplication rule, then we can say that the events A and B, they are independent. So let us assume that the events A and B, they are independent, then priority of A minus. So if the events A and B, they are independent, then we can further expand this in this form. So priority of A into priority of B. So if this happens, here we have assumed that events A and B, they are independent. So we made this assumption. Now let us see what happens. Priority of A, B complement, this is equal to priority of A. So we can take priority of A common from here. So here we have priority A and priority A. If it is common, we are left with 1 minus priority of B. Therefore, priority of A intersection B complement, this is equal to priority of A into, so 1 minus priority of B. So we know that priority of B plus everything that is in B plus that is not in B, that should be equal to 1. We know this relationship. So in set notation, this is equals to B union B complement should be equal to universal set. It's set in terms of set notation. Now, so 1 minus priority of B, this is equal to priority of B complement. So this is again a very interesting result that we have come across. So what did we see? We have assumed that A and B are independent. We found that A and B complement, they are two events, and the priority of their intersection is equals to the product of their individual priority. So we can say that the event A is also independent of B complement, and drawing from this experience we can say that B is also independent of A complement. So if we have two events A and B, and if they are independent, meaning thereby we can write it in this form, and then we say A and B are independent events. Then if we can ensure this, then the ultimate result is probability of A and B complement, they also follow this independence, as well as probability of A complement B, they also follow this independence. So what does this indicate? This indicates that A and B complement are also independent, and this states that A complement and B are also independent. We are going to concentrate on three events. So let us use this property. They are independent. A, B, and C, they are independent. So this means that probability of A intersection B intersection E, C can be expressed as the product of their individual probability, and also probability of A, B, the event A, B, and BC, and then AC, they are also independent. So we can express probability of A in this relationship holds true, probability of C, and then probability of A into probability of C. We assume that this is true. All the three events, they are independent, as well as combination of two of these events are also independent. So in that case, if we construct the event out of any two events, then the event A is also independent of any combination of the event BC. In other words, if this relationship or if this property holds true, then after any event that is independent of the composition of remaining two events. So this is what we want to prove. So we have event A, and let us construct any event out of BC. So let me write B intersection C. So B intersection C is one event. So let us see whether A is independent of this event B intersection C. So this is equal to probability of A and B intersection C. B intersection C is simply BC. So probability of A, B, C. So for the distinction, let us say A is one event, and we have constructed the event, single event, from the event BC. So this is equal to A intersection B intersection C when you use the distributive property. So we know this is the events A, B, and C are independent. It can be expressed as probability of A into probability of B into probability of C using this first property. According to our need, let us use this probability of B into probability of C is probability of BC. So probability of A into probability of BC, and we had started probability of A and we have distinguished it as probability of B intersection C is simply BC. So what did we see? So this is our single event and BC is our single event. The probability of intersection of these two events is equal to the product of their individual probability. So hence we can say that event A is independent of the event BC. Here BC implies BC means B intersection C. Now let us see another example. This time we are taking C as a reference, then after we are constructing an event out of A, B, A union B. So here C is one event and A union B, this is another event. So this is our set notation. We can be more precise by expanding it. So this is equal to C intersection A union B. So we can use the distributive property. So this is equal to C intersection A and then union, and it is C intersection B. So this is equal to C intersection A. It is simply is CA and union, and C intersection B is simply CB. We do not it in this way. So this is equivalent to C intersection A union B. This is equivalent to CA union CB. Now let us take the probability. So the probability of C intersection A union B, this is equivalent to taking the probability of CA union CB, and let me expand it. So this is equal to, let us apply again this formula, probability of X plus probability of Y minus probability of X intersection Y minus probability of X and then intersection Y. Combination of two events ABC, they are also independent. So probability of C into probability of A plus, here we can write probability of C into probability of B minus CA intersection CB. This is equal to probability of C intersection A intersection B. So let me show it in Venn diagram. CA into CB. So here we have CA is this B and D, and CB is D and F. So the intersection is only D. So the intersection is ABC or CBA or whatever name we give it. So this is probability of C into probability of A plus probability of C into probability of B minus this is again, because we know that A, B, C they are independent. So this is equal to probability of A into probability of B into probability of C, and we can take probability of C common. Then after we are left with here probability of A, and here we are left plus we are left with probability of B, and then here we are left with, if C is common, we are left with probability of A into probability of B. So we see that probability of C dot, this is probability of A and then probability of B, and this is indicating that the A and B are independent. We know that events A and B are also independent. That is why we wrote product of their individual probability is the probability of their intersection. Now this is equivalent to probability C dot probability of A plus probability of B minus probability of A intersection B is equal to probability of A union B. Very simple. So what is our starting point? So this is our starting point, and we can say that therefore probability of C, this is intersection A union B. This is one event and this is a single event. We took C is a single event, and out of A and B we constructed an event called as A union B, and the probability of their intersection was equal to the product of their individual probability. That is why we can say that the event C is also independent of the construct of the remaining events A and B. Here we constructed A union B out of AB. So in summary, let us reiterate once again. If A, B and C they are independent, and if their combination AB and then BC and then AC they are also independent, they are individually independent, then if we take any one event, that event is independent of the construct of the remaining two events. Here, if this holds true for any independent events A, B and C, then if we take any one event, let us say A, then that is independent of any construct of the remaining two events B, C. So this is what we wanted to prove. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.